Okay, so good afternoon or good evening to everybody, and I'm happy to give this talk on the AdePT initiative, for which the name basically it's self-explanatory. We are trying to develop a demonstrator for electromagnetic particle transport on accelerators. And I start with the motivation, saying that indeed high energy physics detector simulation on accelerators, it's a hot topic. And I would say it's a hot topic not only because we have to use more GPU resources or accelerators in general connected to HPCs. And I totally share the concerns of Mark, since it's clear that we have more questions on the topic than answers. But I'll be on a more, let's say, optimistic side, and saying that it's hot because also there is a lot of hope. And there is hope because on one side, we are in a much better position than 5 to 10 years ago, when at the time, since then, accelerators have evolved a lot. And we have much more success stories outside the simulation area, like in reconstruction tracking, also in domain-specific simulation, like medical physics, low energy, electromagnetic transport, neutrons, optical photons, and so on. And also, I think that there are many people around who are very enthusiastic of trying a lot of out-of-the-box ideas related to how we can translate the Gen 4 stepping loop to such accelerators. So I will be optimistic about that. So the question is indeed, can we efficiently use the GPUs for more complex simulation applications, like not really only one or two physics processes, but really high energy physics simulation? And at least if we cannot do it at full scale, can we at least handle a big chunk of Gen 4 simulation to the GPUs? For instance, like electromagnetic calorimeter simulation, which seemed a natural candidate, because we could hope that we can get profit from massive parallelism at track level for electromagnetic showers. And this does not mean that we have to run Gen 4 in every single GPU thread, but definitely has to involve transformations and using possibly very simplified or specialized code plus a GPU-specific workflow. Now, this has not started now, so there was a work preempting this effort on GPUs. So even starting with Gen V, which preempted the track level parallelism, and building up features in products like VecGeom, which are supporting natively GPUs. But also there has been work, and it's ongoing work on simplifying and adapting the physics framework to be able to cope with the GPU requirements. So we thought it was a good idea to start a consolidated effort around the prototype within the Gen 4 R&D task force in order to demonstrate a realistic simulation workflow on GPUs and try basically to assess the expectation for performance and for investments in a larger scale project. So it's clear that we are trying a bit to answer the question, can we really do it with reasonable speedups at large scale? Now, the main goal is to demonstrate realistic electromagnetic shower simulation workflow on the GPUs. And since we don't have any recipes telling us how to translate the Gen 4 workflow, we want to start with the simple things first, to start with the basic Fisher-Price workflow demonstrator, trying to simulate only a single particle carrying minimal state with two processes like energy loss and secondary generation, very simple output like energy deposits per cell, but dynamic track population, because the purpose of this first phase is to allow developing a framework that controls a dynamic track workflow, because that's kind of The dynamic part is the keyword that makes a difference between the current successful approaches and what we need to do in simulation, which is governed by stochastic processes, and where basically you cannot start with and use the GPUs for what they were designed for, like you know, processing a fixed size picture. And then once we understand this, the goal is to evolve this as an E plus, E minus gamma simulator in a simple calorimeter setup by introducing gradually more and more components like magnetic field, a transport manager that talks to geometry, evolving the physics processes and allowing to simulate EM showers, and having some output that is reasonable and transferred to the host. The idea is to maintain the CPU compatibility for the entire simulation for obvious reasons. First, for correctness validation, but also for analyzing the performance and having a reference baseline. Now, we have started this like a couple of months ago. So we bootstrapped the AdePT project, like making a repository and putting the basic files there in at the beginning of September. And the work so far was mostly focused on creating some basic infrastructure. Like we thought from the very beginning to separate the part which may be reusable outside what we are developing now, like types, macros, abstractions that could be separated into an externalizable library for GPUs in future, naming that cap core. Developing also concurrent containers and helpers to handle this dynamic population of tracks that we want to be able to handle, and developing some simple examples along the line of this Fisher-Price-like approach, and trying to understand also the different portability strategies in order to be able to run the same code on CPU and GPU. Now the project is kind of rapidly evolving in several directions at the same time. Like in the number of contributors, collaborators, but also contacts with other groups doing similar efforts, because it's not only our project. You will hear this afternoon there are several others. And as work sites, we try to add more standalone work items in order to sort of parallelize the development, because there are many people enthusiasts and wanting to contribute, and yeah, this becomes very important. And we are now moving from workflow ideas to implementation. Now, discussing a bit about the main ideas behind the workflow, we would like to refactor the stepping loop operations as mainly a sequence of kernels. So try to move from a picture where we do list of actions for a track to a list of tracks doing the same action. Then basically try to mitigate kernel synchronization overheads in this sort of chain of kernels, and also thread divergence by trying to overlap the stepping loop execution in multiple streams, in order to be able to try to deal with inefficiencies which are inherent to launching kernels. Then we want to try to partially mitigate the memory latency issues by coalescing accesses for reused state data, like using structure of arrays in the track model, prefetching to share memory for reductions or whatever makes sense, trying to collocate particles prone to execute the same models. In order to be a bit more concrete about this approach, I would just illustrate this with a simple example where you try basically to, it's one of the typical tasks during the stepping loop. You're trying to sample the step length as a competition between several processes registered to particles. And what you would do in the single track CPU approach, which is illustrated in the left part of this diagram, is basically you will start with your track, which let's say it's an electron, and based on the particle ID and on the geometry region, that means material cuts couple, you will fetch a list of processes that applies to that particle. Then you will have a looper on those processes and try to minimize the proposed step length, which is given by this invocation of compute int len for a given track. What you would do on the GPU case is basically you would start with all your electron tracks, and you will have a sort of a kernel that will see them all and basically run the same thing that you run on the SCAR side, like this, get this discrete process list for each of those. And then what it will do, it will just add it to separate lists. You will have a list for a first process, second process, and so on to all the electron processes, which list will become input to a kernel, which is actually computing the interaction length for every single kernel, which will do the reduction at their side. Now, in order to see how this can be actually done, we are investigating some workflow scenarios. And one of those is that, of course, we want to pre-allocate data on device. So dynamic allocations are not very good for GPUs. And in this pre-allocated memory, we want to fit in all the constant data, the state data, which means the tracks, the output data, which are the hits that are going to be transferred then to the host. Then, of course, in this scenario, we would fill tracks from the host and start the stepping loop as this sequence of kernels. And we'll have to manage dynamically selections of tracks for the next kernel to be executed, but also to manage dynamically the new tracks being produced, but also the holes produced by the tracks being killed. So as I was saying, it's very important to think from the very beginning at a dynamic scenario or a dynamic track population. So this control flow, the control will be done using watermarks in the sense that all the allocation of new data blocks, fixing track priorities to avoid memory bloats can be controlled via watermarks. And of course, at the end of the stepping, some of the information will be filled in pre-formatted output hits. Okay, now to speak about some of the topics that we already approached in this R&D. So one of them is the portability. So we are trying out several directions, like portability libraries. We're looking at things like Alpaca, OneAPI, and so on. We're looking at another approach, which is redefining CUDA keywords plus Ellen-like framework kernel launches. And we are looking also at a more like in-house macro-based decoration like we do it in VecGeom, plus a template specialization of the launch API. And I will discuss a bit more about this in the coming slides. Now, the target is to, of course, to maintain a single code base, which runs on CPU and GPU, which has at least a common algorithmic part, even if it's decorated with some macros, and it has a backend specific launch infrastructure, because we want at the end to get the same or compatible results on CPU and GPU. I want to mention here that we are not at all trying to solve the general problem of portability in AdePT. We are really trying to adopt or develop a thin layer, which just requires a minimum development effort and maintenance and just providing the functionality that we need. And as programming model, of course, we have to be friendly to CUDA C++ features. Now, the idea of an idea that we tried is to make an approach which allows kernel launching. So the idea is to hide the CUDA C++ API behind the backend. And this is easy for the function and using function and variable decoration that can be hidden via macros, but not so easy for kernel launches and CUDA types or allocations that have to require some C++ layer on top. So the question was that if we can write a minimal C++ abstraction, and the answer was yes, we could do it in an order of like a few hundred lines, specializing for other backends for the subset of features that we currently use. Of course, this is a sort of a reinvention of the wheel, but we want to keep it very, very lightweight and not to invest more development effort in this thing. The good thing of this approach is that it allows implementing the stepping loop as a chained kernel launches, which are templated on the backend, like it's shown in this picture. So basically, you're trying to abstract the functionality provided by the CUDA C++ API. And in the native approach, which is in the upper part of this diagram, basically the user will write directly kernels, where it will invoke CUDA C++ API, while in the backend aware approach, basically what you do, you just have a launcher templated on the backend, and you call a run function, passing the function plus launch parameters. And then you can have, for instance, for CPU, an implementation which just expands the kernel as a for loop and then uses OpenMP parallelism on top of it. We plan to use also dynamic parallelism. This is due to the stochastic nature of simulation, because we have to have launches for which the parameters are dynamic, and to adapt this to the population of tracks per kernel. And to do that, moving the data from device to host to compute the actual kernel launch parameters is expensive. So we want to make launches basically which spawn the kernel from within another kernel. So this is called dynamic parallelism in CUDA. So basically the example that is shown here, you just have a Compton process for which you just launch a single thread, and the thread on the GPU will actually decide based on the dynamic values of the data which is already on the device, what will be the kernel launch parameters. Now to move forward from where we are now, I was saying, we are splitting the work in more standalone items and tasks because it's important to keep up the momentum and the fact that people are really enthusiastic. And we have identified several such items in several areas, like in geometry, magnetic field, in the data model, memory management, and physics models. And we are gradually adding features to the examples that we have and implementing more complex workflows. Now we try to evolve also the core part to provide a device-friendly infrastructure for physics, like physics and math constants, the materials and guts, random number generator support, and so on. But also working on the track model in order to have these features, like enabling to coalesce the memory, and adding more tools for performance evaluation and benchmarking. And I'll just finish with an outlook that the ADEPT initiative followed an exploration period and discussions that started already last year. And of course, R&D, which started way before that. And we are trying to put together a number of out-of-the-box ideas for particle transport, seen from the GPU perspective. And yes, there are several projects having similar goals, as you will hear after my presentation. I think that exploration is still important and good at this stage where we are still learning, okay? And there is no de facto standard, and now we have to try really different approaches and techniques and learning from other projects. But it's clear that at some point, for engaging a large-scale project, merging the community resources, which are really scarce, will become essential. So we cannot afford developing and maintaining several GPU simulation applications. This is obvious, I think, for everybody. And just on the end note, I would mention that the Excalibur developers are also co-developing in ADEPT. And we have initiated discussions with the Celeritas to touch base on commonalities like geometry and concurring approaches that we are going to discuss in our next meetings. Thank you very much.
Thanks, Andrei. Do we have the chairman online, Jonathan?
Yeah, I'm here.
Oh, okay. So your turn to chair it.
Sorry, say that again?
I guess you're the chairman for the session, Jonathan.
Okay.
So we can take a question now. If Andrea, you have a question.
Okay. Yes, I see John has a question as well, I think. Anyway, my question is just, you mentioned the kernel launchers and the fact that you will have CPU, GPU single source. Now, this is something a bit similar to what we are doing in event generators, I mean, and also what Allen are doing. So I've not understood, is your plan to actually have like a standalone library that different people can use also outside AdePT?
Yes, so the idea is basically to have a set of headers, because basically the implementation is done only in headers, all these launchers. And it's like a very, very thin layer that we can already test and use, and we are going to evaluate it alongside other approaches. It's not like we are trying to define the solution for everybody else, but at least something that we can use in the short term, and that could facilitate the development and comparison with CPU. So it's not like we are aiming so very high, but we are poking around to see how difficult it is to have such a layer, and if it's really very easy to do what we need it for. And that's it.
Thanks.
John, you had a comment?
Yes, it was only a comment that Andrei mentioned that typical GPU applications are not stochastic, and I will agree with that. But there are examples which are stochastic or close to stochastic, and the one that comes to mind is ray tracing, where you send out a set of rays, and where they encounter a surface, they will actually also send out a set of rays if it's done in full ray tracing mode. So that is an example of something that is propagating, not exactly like a SHA, but not completely unlike it either.
Paolo, you a question?
Yes, or a comment. You know, this mention of Andrei of a thin API reminded me of a comment of a former Atlas computing coordinator who said, "Simple API is my API." So the question here is, I mean, is there really value in having this layer rather than, you know, biting the bullet and saying we're going to use Alpaca or we're going to use SQL? Let's not call it one API because that's proprietary.
Well, it's probably early to say it now. I mean, it's clear that we have to spend some time to evaluate all the options for a while. Okay, I would say that for the common current needs that we have in the project, we need something very simple, and the less dependencies we have and the less risk that these will disappear in, I don't know, 2-year scale because of, I don't know, things from CUDA C++ have migrated in the language. I mean, if we could do it in a 2 weeks development and we can use it for 1 year, which is the time scale of this project, I would be happy.
Okay. The only risk is that then you're stuck with it forever, of course, because, you know, once you have 100,000 lines of code with that, then you're stuck with it forever.
Well, it's not. I will not be so worried in the sense that indeed there may be some macros that look differently than the macros in Alpaca or one API, and there will be maybe one allocator which looks a bit different. But at the end of the day, this is really just the calling sequence. The bulk of the code will basically stay untouched.
Okay.